section 7.3, Gauss elimination, which is a very basic algorithm for solving non-singular algebraic system. The algorithms developed in this section will produce the unique solution of the given algebraic system. Only possible difference can be a rounding error. Here we have a strategy for Gauss elimination. First, we transform the given system to an equivalent system, which is an upper triangular system. That part is for the elimination. Then we further transform the system to get the solution X, which is the back substitution. It is convenient to represent the system by an augmented matrix, and the transformation of the system can be done by means of 3 elementary row operations applied to the augmented matrix. We define elementary row operations. Replacement is defined in this way. Row is replaced by adding a multiple of another row. Interchange is simply interchange 2 rows, ith row, jth row, and scaling is now a multiplication of non-zero scalar. These 3 elementary row operations are the quite basic but very useful and fundamental operations for matrix manipulations. If A hat B hat is an augmented matrix, is obtained from an original augmented matrix by elementary row operations, then these two systems will have the same solution. Elementary row operations will not change the solution, so they are equivalent. Suppose A is obtained from a matrix A by elementary row operations, then A hat is non-singular if and only if A is. So there also singularity and non-singularity will be preserved by the elementary row operations. Each elementary row operation corresponds to left multiple of an elementary matrix. The operation can be done by multiplying the corresponding elementary matrix in the left side. Each elementary matrix is non-singular. You can see it quite easily. It is invertible. Alpha times of Rj is added to ith row, then alpha times of Rj is subtracted, then its inverse. Interchange its inverse is itself one more time, then it will go back to original 1, and also beta scaling for this one, because beta is non-zero. If you multiply 1 over beta, then it will go back to the original 1, which means that every elementary row operation has its own inverse, which means that elementary matrix is non-singular. The elementary matrices correspond to replacement and scaling operations are lower triangular. And interchange is not lower triangular. but for replacement and scaling operations, the corresponding elementary matrices are lower triangular, and also multiplication of lower triangular matrices will be again lower triangular. So that overall, the combined operation using replacement and scaling will be lower triangular. Okay. Now we consider here the LU factorization or LU decomposition. LU factorization is motivated by the fairly common industrial and business problems of solving a sequence of equations, particularly multiple right-hand side. And for the system, now right-hand side input is changing and various input comes, and then you have to solve it again. But rather than apply inversion for each right-hand side, we can make LU factorization, and then now lower and upper triangular systems can be solved much more efficiently for each right side. So it is quite common in real world. Now, the LU factorization is defined for general size matrices, and A is in n by n dimensions, and the LU factorization of the matrix is now LU. L is m by m, lower triangular matrix, and unit means that along the diagonal, the entry is 1, and U is on echelon form, which means an upper triangular matrix, okay, like in this one. Now, here we assume that we have to solve AX equals B. Then, along with LU factorization, AX can be written as LUX and right-hand side B. Then we can solve this system easily in 2 steps. First, we define this portion is Y. Then now we can invert L to get Y. And Ly equals Y. Lx, okay, Ux equals Y. For this equation, by inverting U, we can get X. Okay. So by using the fold elimination and back substitution, we can solve the problem quite easily. That's the reason for multiple right sides. We try to make LU factorization once and use it again. Also, we know that LU, this solve a lower triangular system and upper triangular system. Solving these systems is optimal. It requires a minimum possible cost, so that after LU factorization later on, it is really super efficient. Okay. Now then, how can we get LU factorization? So we have here an algorithm. The derivation introduces on LU factorization for A general size n by n dimensions. Okay, we start with an identity matrix in front of A. If you multiply this identity matrix, then the result will be the same as A. Now, in Gauss elimination, basic, in Gauss elimination. The basic idea is if we start with this pivot, then we try to make the below the pivot 0, 0, 0 like that, so that when you start Gauss elimination, you have to transform the matrix into an upper triangular matrix. So we have to eliminate this portion that is corresponding to a elementary row operation, and also it can be written as elementary matrix. So here we multiply, for example, E1 to eliminate that entry. Then we apply E1 to A. Now we apply E1 inverse. Then eventually, by canceling, we have the same result. So equality holds. Okay. Now, if we try to eliminate this one, then we have to apply another one. Let's say, which is E2. Then again, E2 inverse is there. So that again is equal, and so on. So that in the last moment, we try to eliminate everything below the diagonal, and then we may reach this position. So that from E1 to EP, there are P elementary operations to get upper triangular matrix. Of course, that is on echelon form. Now, their inverses are putting there, but we can reorganize this one into this form. So that is E1 to EP. Now, this portion is E1 to EP inverse. If we use only replacement, then it'll be a lower triangular matrix, and its inverse is also lower triangular matrix. So we have this portion L. Now, for the elimination makes upper triangular. So we reach at LU factorization. Okay, that's the strategy. Now, you can find LU factorization quite easily. Start with identity matrix in front of A, and then try to eliminate this one. To eliminate this one, now twice must be added. So, just added. But its inversion is subtracted. So that is now -1. Now twice is subtracted to eliminate this one, so that in the elementary matrix, -2 will appear. Its inverse is add twice of this one, the first row. So its inverse has that entry. So you can figure out the early factorization of the given matrix is these two matrices. Okay, you can do it yourself. Now we have a theorem for LU decomposition. The following are equivalent. Okay. Now all leading principal submatrices of A are non-singular, and this claim, the assertion is the same as this one. There exists a unit lower triangular matrix L and non-singular upper triangular matrix U such that A is LU. Okay, for this one, of course, we have to start with A is square matrix. Okay. Now, principal matrix. Okay. A matrix is given, then consider its diagonal. And principal matrices are matrices including the original diagonal entries. as diagonal. So that, for instance, if we select this portion, then this is a principal submetric. And you can get various way. Now, leading means that it is including this A11, so that leading principal submatrices are these matrices. For example, this one. And also, one entry itself is a leading principal submetric. Also, for example, like that, this whole thing is also a leading principal submatrices. Among principal submatrices, once the leading entry is included, then that is a leading principal submetric. Okay? So all of these leading principal submatrices are non-singular, which is the same as now the L factorization, the existence of L factorization. For L factorization, now pivoting is not required. Once pivoting is required, then A cannot be written as L factorization. Once when you are working on the Gauss elimination, then at some point, if you made a zero pivot, then without row interchange, you cannot go further. So once it is happening, then there's no L factorization. The existence of L factorization is now the case that without any row change, row interchange, you can get LU factorization. Okay, that is equivalent to this assertion. The theorem is proved roughly. So if you are interested in mathematical proof, then try to read it. Okay, we have an example. Now, find the L factorization of a matrix, and we can implement in this way. A is given, then output will be again the same, the memory for A. In order to do that, for example, now we measure the ratio so that to eliminate this one, we have to subtract 3 times of first row. So at this position, the -3 is the elementary row operation, but its inverse must be +3. So that is now for L +3. And so eventually, and elimination is subtract the along with the ratio. Now, its inverse is add along with the ratio, which means that the L in L, just the ratio is used. So ratio is -2, and that is the same as now third row is replaced by third row plus twice of first row. And inversion of that is -2 Ri, so that we have here -2. Okay, after finish this one, of course, when you try to do that, each operation, then 3 times of R1 is subtracted, so that it is 0. So for 0 position, we save its inverse, and 3 times subtracted, so that it becomes 4. 3 times subtracted, so it becomes -1. Also the same for that one. Twice added, so it's 0. Now we put here inverse, and then twice added, so that in -2 is here added, so it becomes 3. twice added, so it becomes minus 3, right? Now, we finished for this first column, and pivot is moved here, and the ratio is now 3/4. So we have here, and 3/4 times of this second row is subtracted, so that from minus 3, it is changed into this one. Now, that is output, which means that L is, along with this lower, strictly lower entries and diagonal 1, this is L, and including the main diagonal, upper portion is U. Okay? So you can easily verify that if you multiply these two matrices, then you can get A. Now also, for tall matrix like this one, and you can apply LU factorization exactly the same manner. We'll try to eliminate this one, that one, that one. Now its inverse will have ratio. There's 3, minus 5, and 6. Of course, this will be correspondingly changed, replace them. And after finishing this first column, now pivot is here, moved here, and then ratio over there, so that you can get here lower triangular metric and upper triangular metric. Always lower triangular metric is square along with diagonal 1, and U has upper triangular metric on echelon form, right? U has the same size as A, while L is a square metric and is a unit lower triangular metric, as you observed from this example. Okay, for an n by n dense metric A, and the dense metric means that most entries are non-zero. And here, when n is moderately large, then computing an LU factorization of the metric takes about 2n³ / 3 flops. And it's you can get it quite easily. And now, while if you try to find A inverse, then it is a bit more expensive. So solving, now Ly equal B and Ux equal Y, which means that solving after LU factorization, solving triangular systems requires about 2n flops. And so that even though, okay, after LU factorization, and okay, let's begin with this one, AX equal B. You can solve this one first, and LU factorization, and then now L solve and U solve. You can do that. And here, and secondly, you may try to get, for example, A inverse first, and then try to invert to solve that one. Right? You can do either way. So we are trying to compare the computation cost for these two cases. Now, LU factorization itself is taking this computational cost. A inverse requires more. Now, solving here, this two system requires 2n² flops. Now, once A inverse is computed, but solving so that, for example, here A inverse B to get X, this one must be multiplied in front of b. Then this one requires also 2n squared flops, because that one is n by n square metric. There are n squared entry, and this one is each row and be dot product. So for each entry, it requires 2 operations. So eventually, this multiplication itself requires about 2n flops. So the solving these 2 triangular systems or multiplication of A inverse, they are almost the same. And so that using this second method is not much advantageous. Even here, tensor metric case. Okay, how about the metric is sparse and only a small number of entries non-zero, and for example, like in banded metric, or even though it is not banded metric and here sparse, then now LU may be sparse. LU is not really the full matrix. On the other hand, A inverse will be most likely a tensor matrix. Okay, that is a physical reason why A inverse is likely to be dense. Okay, let's see this example. For example, we simply consider one-dimensional domain. Now, we assume that this system is corresponding to a stationary solution of heat transfer, for example. Then here, from this one, now X is a inverse being, okay, some source, and then, but here, if you change a temperature, for example, at a point increase, okay, temperatures increased, so that here one entry on the right side is changed. Physically, temperature increase at a point will make every temperature increase, which means that now when you multiply this and that, and that means that every is connected, so that to get every increase, and it must be a kind of dense metric. Without that, maybe somewhere is 0 when, okay, now A inverse itself and then somewhere is 0 appears, then the corresponding right-hand side change will not make the increase, so that it cannot be 0. Particularly for heat transfer, this A inverse must be always positive. There's no entry, no 0 entry. Every entry must be positive. Temperature increase must be every positively the change. Positive change must be guaranteed. That is physical the truth, so that and A inverse must be given that way. Now, so that here for LU factorization for original matrix sparse, the LU can be sparse. However, A inverse is most likely dense. That means that now when you try to solve the problem along with LU or A inverse, then A inverse must be much more expensive. So that there is no benefit using A inverse. So rather than that, you can use LU factorization and you can enjoy efficiency. Okay, here we have a summary. Once you make LU factorization, then now for n by n square metric and non-singular, once you can get LU factorization, then AX equal B can be written now here LUX, but first for UX we consider that is Y, then that is LY equal B. So first we solve LY equal B, this lower triangular system, and then in order to get the target, we solve the upper triangular system. Okay, so LU factorization is better than using A inverse. Okay, now we are trying to solve AX equal B. A is given, B is given in this way. Also, LU factorization is given. We'll try to use the LU factorization of the matrix A to solve the system. First, we can solve LY equal B, and later on UX equal Y. In order to do that, now L metric and here B, so it's augmented metric, and then by applying elementary row operations, now that is now the result, the rightmost column must be Y, and we put this Y over there, and this is U metric. Again, we multiply row operations, and so that it becomes identity, and this last column must be the solution. Also, we have another example, the same A. Now, A is LU factorized there. Then, first we can solve LY equal B. This is L metric and right hand side B, and we apply now elementary row operations to get Y, and along with Y, this is U, and here once more, along with elementary row operations, we can get the solution X. Okay, that's the end of the section. Thank you.